This meeting is being recorded.
In Chapter 19, we're now going to take a look at what's referred to as electrochemistry. And we can define electrochemistry or just electrochemical reactions even more generally as reactions when electrons are transferred from one species to another. So you may recall that oxidation and reduction reactions include either losing or gaining electrons, and you are correct that electrochemical reactions do involve reduction and oxidation. So let's take a look and review some of the rules that we saw in General Chemistry 1 when we referenced oxidation number, oxidation state, and then how to identify whether or not a reduction or oxidation reaction is happening. So in oxidation, if you recall, you will lose electrons. By that, your oxidation number would increase. So we increase oxidation number. That's why it's called oxidation. And if you remember, you can generalize this as oxidation is losing. We could say oil here. And then reduction by gaining electrons, as we see over here, our oxidation number will go down. And we can say that reduction is gaining. So this is one kind of mnemonic device here, this oil rig, to remember that oxidation is losing and reduction is gaining. Or you can use another, you can say losing electrons is oxidation and gaining electrons is reduction. So this one also works, Leo Ger. So now that we've refreshed our memories, we see an example here of an oxidation reaction. So our solid copper in its elemental state there would have a 0 oxidation number. And then over here, we see on the product side that it has been dissolved in water. It's now aqueous. It's now an ion. So we see that its oxidation number will be that of +2, the same as its charge, and it has lost 2 electrons. When we write these half reactions for oxidation and reduction, we can think of the electrons as being either products, as the case with oxidation, or a reactant, as in the case with reduction here. We see this example of reduction where the silver, the +1 ion, so that has a +1 oxidation state, is being reduced by gaining the single electron to a 0 oxidation state. So if we were to shorthand this, we could say that the oxidation state of copper goes from 0 to +2. So we see that's definitely an oxidation, an increase in oxidation number. And then here we go from the silver being +1 back to 0 or down to 0. So that's definitely a decrease in oxidation number or a reduction. So we're going to see these split into half reactions, but if we have mixed the chemicals into the same container, oxidation and reduction will be happening in the same beaker. We're going to see that when we have these things called voltaic cells or a spontaneous movement of electrons, that we're going to kind of separate these two oxidizing and reducing reactions, one from the other. So we'll see that coming up. But next, we should also note that whatever is being reduced, that's going to have a lowering in oxidation number, will be considered the oxidizing agent. So it's going to gain electrons, therefore it's going to take electrons from something else. So therefore it's going to oxidize something else. So we call that the oxidizing agent. And then the opposite of that, whatever's being oxidized can reduce something else. Because that's going to be losing electrons, so those electrons can be gained by whatever the other species is. All right, so now that we've reviewed that, let's take a quick look at how we know what numbers we memorize our oxidation numbers here, and then which numbers we would have to solve for. So any elements in their elemental form will have an oxidation number of 0. So this includes elemental metals like magnesium, iron, elemental carbon, etc. Or we could have the diatomic elements such as H2 gas, N2, etc. Any of these are in their elemental state, and we would assign these oxidation number of 0. Whenever we have a monoatomic ion, it's going to be the same as its charge. So magnesium in its ionic state will have a +2 charge. Like so, we would see lithium will be +1, potassium +1, etc. Then we have nonmetals, and those things that we can remember here with oxidation numbers. Rarely are nonmetals going to be positive, only in certain compounds or ions. So for example, we have oxygen here. For our purposes, this will always be -2. There is one exception when it has an oxidation number of -1 when we see peroxides, but we probably won't encounter these. But something like H2O2, hydrogen peroxide, oxygen will be -1 in that specific case. But again, for our purposes, we can think of it as being in group 6A, if you remember. That would gain 2 electrons, so it would have a -2 charge. So we generally say we have O2 negative. Hydrogen, it's only -1 in the case when it's bound or bonded to a metal. So say we have sodium hydride here. In that case, our sodium is +1 oxidation state. Our hydrogen here would be -1, again, in only that rare scenario. So for our purposes, most of the time, all of our hydrogen will be a +1 oxidation number. We're going to see fluorine always has an oxidation number of -1. The other halogens may. So when they're in binary compounds, so we'll see fluoride in the case of HCl, that's a binary compound. And other scenarios where we have bromide or iodide only bound to one other element, they all have a -1 oxidation number, but at times, say we have an oxyanion, for example, say we have ClO2 negative here, this chloride, this will actually have a 3+ oxidation number, because we know that this is a -2 per oxygen, so that gives us -4. We have a net -1 charge here, so this must equal +3. So if we wrote that out algebraically, we would see 2 times -2 here, gives me that -4 +3 will equal that net -1 charge. All right, so on that note, that's a polyatomic ion. So a combination of multiple elements together has an ionic charge. In this case, it's an anion. But most of the time, if we have a neutral, or all the time, if we have a neutral compound, all of our oxidation numbers, when we add them together, the sum of them has to equal 0. So in the case, we can see HCl, if we have a -1 here, we must have a +1 here, and vice versa. Together, they equal 0. The sum of oxidation numbers on a polyatomic ion, like we saw over here, is the sum of the charge, so -1. All right, so now that we've reviewed all this, let's take a look at exercise 1 here and see if we can assign the oxidation numbers to these species. Specifically, we're going to solve for whatever element we don't have a rule for. So let's set up an algebraic expression here. We're going to set everything equal to -1 because this has a -1 charge. We generally do not know manganese, the oxidation number, because that can have various oxidation states, being that it's a transition element. So we'll just use manganese as our variable here to solve for. Then we have 4 oxygens, each of which is -2. So all of this together, we already have our equal sign, so we're going to say here -1 equals manganese plus -8. So I'm going to add 8 to each side. So this manganese then will have a +7 oxidation state. Let's take a look at sulfur in this next example. Again, we have a rule for oxygen, so we're going to now set this equal to -2. We're going to solve for sulfur, but be careful, we have two of them. So we're going to put in 2s here as our variable to solve for. That way we know that we have to divide by 2 at the end of our equation here. And then we have for each of the 3 oxygens a -2 charge. So now we have, if we write this out here, -2 equals 2s minus 6. We'll add 6 to each side. So now we have our 2s equals +4. We divide by 2. This sulfur has an oxidation number of +2. All right, last but not least here, we have our, oh, wait, we have 2 more. So C is fairly quick and easy. We just look at the charge of our monoatomic ion. So we know that in this case, manganese has a different oxidation number of +2. And now, last but not least, we'll solve for sulfur once again. We only have 1 here. So we're going to set everything equal to -2, solve for sulfur, and then we have 4 times -2 for oxygen. So we get sulfur minus 8 equals -2. We're going to add 8 to each side here. So we're going to see that sulfur now has an oxidation number of +6 in this polyatomic ion.